Hey guys, welcome back. In this session, I will be discussing on software-defined vehicles, and these are the topics I will be covering in this video. I will start with the introduction to software-defined vehicle, software-defined vehicle architecture, core software layers in software-defined vehicles, software-defined vehicle enabling technologies, then software-defined vehicle development lifecycle. Then we will look into some real-world software-defined vehicle examples. Then I will discuss challenges and opportunities in software-defined vehicle, then mini project or hands-on demo, then at the last summary and bonus content. So these are the topics which I will be covering in this video. Let's get started. Let's begin with a simple question. What is a software defined vehicle or SDV? Traditionally, vehicles were controlled by hardware like mechanical systems, some basic electronics, and individual control units for specific functions. But an SDV changes that. In an SDV, software becomes the core of the vehicle's intelligence. It's not just about adding infotainment or navigation systems, it's about making the vehicle capable of updates, improvements, and even new features all through software. Think of your smartphone. You don't need to change your phone to get a new feature. You just update the software. Software defined vehicles bring the same flexibility to your car. From safety to performance, from entertainment to energy management, software is now in the driver's seat. Let's take a quick journey through the evolution of vehicle technology. In the early days, vehicles were fully mechanical. Everything was done through gears, levers, and hydraulics. Very little to no electronics. Then came the electronic era. Microcontrollers and ECUs or electronic control units were introduced to help control engines, brakes, airbags, and more. Each function had its own small computer. Now we have entered a new era, the software defined era. Instead of many small ECUs working separately, software runs across powerful central computers, enabling smarter integration, connectivity, and automation. This change is huge. It's not just a tech upgrade, it's a complete shift in how vehicles were designed, built, and even maintained. Software defined vehicles allows manufacturers to fix bugs, add features, and enhance safety even after the car is sold without needing a recall. So, how does an software-defined vehicle differ from traditional vehicles with the ECUs? In traditional cars, every feature is tied to a separate ECU. If you want to upgrade, you need a new hardware. If something breaks, you replace the part. In software-defined vehicles, many functions are virtualized and run on a centralized computing platform. That means less hardware, more flexibility. Also, in traditional systems, updating anything often requires a visit to the service center. In software defined vehicles, update can happen through over the air just like your phone or laptop. Security is also improved. With centralized systems, you can build stronger, more consistent security protocols across the entire vehicle. In short, software defined vehicles are smarter, safer, and more future ready. Let's start with vehicle architectures, specifically domain and zonal architectures. In traditional domain based architecture, the vehicle is divided into domains like powertrain, body, infotainment, chassis, and ADAS. Each domain has its own set of ECUs and controllers. The challenge, it leads to increased wiring, complexity, and cost. Communication between domains can be limited and software integration becomes harder. Now, with the software defined vehicles, we move towards zonal architecture. Here, the vehicle is divided based on physical zone, front left, rear right, center, and so on. Each zone has a zonal controller that handles inputs from sensors and actuators in its area and communicate with the central computer. This approach reduces wiring, simplifies diagnostics, and make the system more scalable and serviceable. In summary, zonal architecture is the future. It's more efficient, modular, and software friendly. Now let's talk about the brains of software defined vehicles, high performance computer or HPCs. Instead of dozens of small ECUs, software defined vehicles use one or more powerful central computers that run multiple vehicle functions in parallel. These HPCs offer massive computing power similar to what you find in a server or even a gaming PC. Well, why do we need them? Because modern features like ADAS, autonomous driving, AI based decision making, and over the air updates demand real time processing and data handling. Central compute platforms bring several benefits, like they reduce hardware cost and weight, improve speed and data sharing, allow software updates from the cloud. In software defined vehicles, HPCs are the art, enabling a software first, hardware light approach. Just like your laptop needs Windows or Mac OS, a software defined vehicles needs a vehicle operating system. Let's look at a few major OS platforms. First is Linux. Open source, highly customizable, and already used by many companies like Tesla. It supports fast innovation and over the air updates. Second is QNX, a commercial real time operating system known for safety, stability, and certification, often used in mission critical issues like ADAS and infotainment. Third is adaptive AUTOSAR, designed specifically for software defined vehicles. It supports dynamic software management, high performance computing, and service oriented architecture. Each OS has its role. Linux is flexible, QNX is reliable, and adaptive AUTOSAR is standardized for automotive. Together, they enable the multi OS ecosystem needed in software defined vehicles. Finally, let's discuss in-vehicle communication, the digital conversation between ECUs, sensors, and computers. First, we have CAN, Controller Area Network. It's the most widely used protocol, great for real-time short messages like engine control or brake signals. Next is LIN, Local Interconnect Network. It's slower but cheaper, used for things like window controls and mirrors. Then comes FlexRay, faster and more robust, often used in safety critical systems like advanced driver assistance. Now we have Automotive Ethernet, the game changer. It allows high speed data transmission, ideal for cameras, LiDAR, infotainment, and cloud connectivity. As software defined vehicles grow in complexity, Ethernet will become the backbone of in vehicle communication, enabling the software driven feature. In short, communication inside the car is evolving from slow and simple to fast and intelligent. Let's begin with the application layer, the layer you, the driver or passenger actually experience. This is where all the features and functions of a software defined vehicle live. Some key examples include ADAS or Advanced Driver Assistance Systems like lane keeping, adaptive cruise control, and emergency braking. HMI or Human Machine Interface. This includes digital dashboards, voice assistants, and gesture controls. Infotainment systems, things like music streaming, navigation, and smartphone connectivity. What's powerful here is that all these applications can be updated over the air, enhanced, or even entirely replaced, just like updating an app on your phone. This layer is constantly evolving to make your driving safer, smarter, and more enjoyable. Now let's look under the hood at the middleware layer. This layer acts like a bridge between the application layer and the hardware. It ensures that different systems can communicate or talk to each other smoothly and securely. Some popular middleware technologies used in software defined vehicles include SOME or IP, also known as Scalable Service Oriented Middleware or IP, commonly used in automotive for communication between ECUs and services. DDS, Data Distribution Service, used in autonomous systems for fast, reliable data sharing between multiple software components. MQTT, Message Queuing Telemetry Transport, a lightweight messaging protocol often used for cloud to vehicle communication. Middleware ensures that all apps, whether handling brakes, navigation, or AI, work together without conflict, even if they come from different vendors. Next up, the foundation layer, BSW, Adaptive AUTOSAR, and Hypervisor. Let's start with the base software, BSW. It includes drivers and services that talk directly to the hardware, like timers, memory handlers, and I/O drivers. Then comes Adaptive AUTOSAR. Unlike classic AUTOSAR, which was static, Adaptive is dynamic, service-oriented, perfect for HPCs in software-defined vehicles. It supports features like over-the-air updates, parallel processing, and even real-time safety systems. Now, hypervisors. These are like digital managers. They allow multiple OS or software stacks to run safely on same hardware. For example, you can run a Linux-based infotainment system and a safety-critical QNX system on the same chip without interferences. This layer makes software-defined vehicle modular, flexible, and secure, enabling next-gen mobility. Finally, let's explore the connection between the car and the outside world, cloud and edge integration. In a software-defined vehicle, car is a no longer an isolated machine. It constantly communicates with the cloud for updates, diagnostics, and learning. From navigation data to vehicle health, everything can be synced and improved using cloud computing. Then comes edge computing, processing data at the vehicle level without needing constant internet access. This is useful for time sensitive functions like collision avoidance or object detection. The mix of cloud and edge gives software defined vehicles the power to be smart, connected, and continuously improving even after they leave the factory. Let's begin with over-the-air updates or OTA. In past, updating a car's software meant visiting the service center. With software-defined vehicles, that's changed forever. Now manufacturers can send software updates wirelessly, just like how your smartphone updates overnight. These updates can fix bugs, improve performance, and even add new features after the car has been sold. For example, Tesla once added better acceleration and braking through a software update. No hardware changes needed. Over the air also allows security patches to be deployed quickly, reducing the risk of hacking. And it's not just the infotainment system, ADAS, battery management, and even suspension can be updated over the air. In short, over the air is what makes the car a living, evolving product, not just a machine you buy once. Next, let's talk about digital twins and AI ML. A digital twin is a virtual replica of your physical car running in the cloud. It mimics the behavior, health, and performance of your vehicle in real time. Why is this useful? Engineers can simulate upgrades, predict failures, and test new features without touching the real car. Now combine this with artificial intelligence and machine learning, you get a car that can learn from your behavior. For example, the AI can learn your driving habits and suggest routes, adjust seat positions, and even control energy usage based on your style. It also helps with predictive maintenance. The system knows a component is about to fail before it actually does. Digital twins and AI make software defined vehicles smarter, safer, and more proactive. As vehicles become more connected and software defined, cybersecurity becomes critical. Imagine if someone could hack into your braking system. That's a risky we must avoid. That's where secure bootloaders come in. A bootloader is a piece of code that runs when the car starts. A secure bootloader checks if the software is authentic and untampered before loading it. If something's off, even one line of code, it stops the process. Beyond that, software-defined vehicles use encryption, firewalls, intrusion detection, and secure communication protocols to protect data. Cybersecurity is vital for over-the-air updates. If a hacker intercepts an update, they could inject malware. So strong authentication and encryption must be in place. Cybersecurity makes sure software defined vehicles are not just only smart but also safe and trusted. Lastly, let's talk about vehicle personalization and data logging. Today's software defined vehicle is no longer a one size fits all machine. It adapts to your profile, seat position, mirror angles, music preferences, even climate settings can be saved and automatically applied. Even more exciting, personalization can follow you across different vehicles like a digital driver ID. Now, data logging collects vehicle information in real time, like speed, battery status, sensor inputs, and system health. This helps in diagnostics, predictive maintenance, and improving future vehicle designs. All this data, when used ethically and with privacy controls, helps make the car smarter, safer, and more enjoyable for the driver. Let's begin with the CI or CD and DevOps, two buzzwords from the software world that are now reshaping the automotive industry. CI stands for continuous integration. It means that developers are constantly merging new code into a shared platform. Every small change is automatically tested. CD stands for continuous delivery or deployment. It ensures that every code update can be delivered or released fast and safely. When applied to automotive, this means software updates can be tested, validated, and pushed to vehicles faster than ever before. DevOps bring together developers and operation teams to streamline this entire pipeline. In software-defined vehicles, DevOps enables over-the-air updates, real-time bug fixes, and faster delivery of features. This makes development more agile, automated, and scalable, a key shift for modern vehicles. Now let's talk about virtual ECUs and model-based design. A virtual ECUs is a software version of a physical ECU. It behaves the same way but runs on a PC or server. Why is that useful? You can test and validate features before the hardware even exists. This speeds up development and reduces cost. Now add model-based design, which means we build graphical models of control systems, simulate them, and then automatically generate code. Using tools like MATLAB Simulink, engineers can design, simulate, and test systems like powertrain or ADAS early in the process. With MBD and virtual ECUs, developers can explore what if scenarios, fix bugs early, and reduce risk. This combination leads to faster, safer, and more accurate development for software defined vehicles. Next, we dive into testing methods that power software-defined vehicle development. Mill, SIL, and HIL. Let's start with MIL, model in the loop. Here we test the logic using mathematical models in simulation. No code needed yet. Then comes SIL, software in the loop. Now we test the actual code, but still it runs on a computer, not real hardware. Finally, HIL, hardware in the loop. This is where real ECUs are tested with simulated sensors and actuators. It gives real world feedback without using a physical car. Each step builds on the previous, allowing you to test early and fix issues before they reach the vehicle. These methods ensure high quality, safety critical software is developed in a structured, efficient, and error free way. Finally, let's talk about the tools that make software defined vehicle development possible. Vector tools help with the simulation, communication analysis like canoe and diagnostics. ETAs offer embedded solutions for real-time testing and development. DSpace is a powerful for ill testing, rapid prototyping, and virtual ECUs. MATLAB Simulink is a go-to for model-based design, control logic modeling, and code generation. Each of these tools plays a vital role at different stages of the software-defined vehicle lifecycle, from modeling and coding to testing and validation. Together, they support a faster, safer, and smarter development journey. Let's start with the two leading examples of software-defined vehicles, Tesla and General Motors Ultifi. Tesla is the pioneer of software-defined vehicles. Unlike traditional automakers, Tesla builds the car around software from day one. They use a centralized computing platform, so updates are seamless across the entire car. Everything from acceleration to autopilot features can be improved over the air. Tesla also uses real-time data logging and AI to improve its systems daily. Now GM's Ultifi is their answer to Tesla. Ultifi is a software platform that separates software from hardware, enabling faster development and updates. It allows developers to create apps and services just like on your smartphone, creating a personalized experience for each driver. Tesla and GM are providing that software defined vehicles are not just the future, they are the present. Next up, let's look at Volkswagen's Carrier and Mercedes-Benz MB.OS. Carrier is a group inside Volkswagen working to unify software across all its brands Audi, Porsche, Volkswagen, and more. Their goal is to create a single software platform for all vehicles, which simplifies updates, services, and security. Carrier is focusing on ADAS, autonomous driving, and over the air functionality. While they have faced delays, the ambition is to own the software stack, not depend on suppliers. Now let's look at MB.OS, Mercedes-Benz operating system. Unlike others, MB.OS is a purpose-built OS created fully in-house. It allows deep integration with navigation, infotainment, powertrain, and more. MB.OS also connects with the cloud and third-party apps like Google Maps or even YouTube. This platform is about luxury through personalization, a seamless high-end experience powered by software. Well, Carrier and MB.OS show how legacy automakers are transforming into tech companies. Finally, let's look at some emerging players and platforms shaping the software-defined vehicle future. Companies like Aptiv, Canoe, Rivian, and NIO are designing vehicles around software from day one. These companies are nimble, fast, and often adopt a cloud native mindset, making their vehicle easier to adopt and personalize. We also see tech companies entering this space. Google's Android Automotive, Apple CarPlay Next Gen, and Amazon's Alexa Auto are becoming part of in-vehicle ecosystems. Plus, platforms like BlackBerry QNX, NVIDIA Driver, and Qualcomm's Snapdragon digital chassis are powering the software-defined vehicle brains behind the scenes. Together, these companies are reshaping what a car can be, a software powered smart device on wheels. Let's start with the challenges that come with software defined vehicles. First, we face major technical challenges. One of the biggest is software complexity. A modern software defined vehicle can have 100 million plus lines of code, more than a jet or smartphone. Managing that code, keeping it secure, and testing it thoroughly is not easy. Next is hardware software decoupling. Moving from traditional ECUs to centralized compute means the whole system architecture must change. That's a huge shift. And another challenge is real time performance. In a software defined vehicle, systems like braking, steering, and ADAS must respond instantly, no delays allowed. So, the software must be highly optimized and tested. Now, let's talk about regulations. Well, with software controlling critical driving systems, governments are now demanding strict cybersecurity, functional safety, and update compliance. You can't just ship a buggy code and fix it later. Safety is non negotiable. Plus, different countries have different standards, making global deployment tricky. In short, the path to software defined vehicles is exciting, but full of complex technical and legal obstacles. Future trends and career opportunities in software defined vehicles. The trend is clear. Cars are becoming smartphones on wheels. You will see more centralized compute platforms, edge AI, and autonomous features integrated into the software stack. 5G connectivity, vehicle to everything communication, and cloud edge fusion will enable smarter connected driving experiences. As a result, automakers will need more software engineers than mechanical engineers. Now let's talk about careers. If you are from electronics, computer science, electrical, or mechanical backgrounds, there is space for you. Key areas to explore include embedded systems development, model based design using tools like MATLAB Simulink, AUTOSAR, both classic and adaptive, cybersecurity and over the air updates, cloud, DevOps, and backend integration of cars. Also, testing roles like Hill, SIL, and Mill are growing fast. If you understand CAN, LIN, Ethernet protocols, and tools like Canoe, DSpace, and ETAS, you are in demand. In short, software defined vehicles are not just transforming cars, they are creating a new world of engineering careers. Now is the time to skill up and ride this wave. Let's look at some project ideas. You can use either Canoe or MATLAB Simulink to simulate a simple software-defined vehicle communication setup. Imagine a smart car with a brake ECU, a display unit, and a central controller. Our goal, when you press the brake, the controller sends a signal to the display saying brake applied. In Canoe, we can simulate the nodes, add message frames using CAN database DBC files, and visually track message flow in the trace window. We will configure two nodes, one sending the brake signal and other receiving and displaying it. You will learn how to define CAN messages, adjust timing, and simulate conditions like message delay or packet loss. Now, if you are using MATLAB Simulink, we will create two blocks in Simulink, a brake sensor simulation and a signal processing logic. We will visualize data with a scope block and simulate how the signal behaves under different conditions. This gives you a taste of how engineers test and validate ECUs before going to real hardware. Even better, these skills are used in Hill hardware in the loop testing environments every day in the industry. Now let's look into a basic over-the-air update project idea. You don't need a car, just your computer and some logic. Let's say you have a Python script that simulates an ECU software version. We will create a local server that hosts a new firmware version. The ECU script will check for updates every second. If it finds a newer version, it will download and install it. The log will show something like this: checking for updates, update found, downloading, update complete, restarting ECU. This mimics how real vehicles receive and apply software updates remotely. It helps you understand OTA logic, version management, fallback strategy, and basic cybersecurity concepts like secure download and verification. You can even use tools like Postman or MQTT to simulate cloud interactions. Finally, let's understand middleware signal flow, especially SOME, IP, or DDS. Imagine your car has multiple apps running. One controls the climate, another displays maps, and another monitors sensors. They need to talk to each other, but not directly. That's where middleware comes in. With SOME or IP, these services are published by one module and subscribed to by others. It's like Netflix, one system streams and others receive. In a demo, you can simulate this using Python sockets or tools like ecal or RTI DDS. You define a simple service like get temperature, and another module can subscribe to that and show the output. This is the foundation of modular service based vehicle software, and it's a game changer for software defined vehicles. Let's quickly recap what we have learned in this course on software defined vehicles. We began with these basics of software defined vehicles, its evolution, and how it differs from traditional automotive architectures. Then we explored zonal versus domain architectures, high performance computers, and in vehicle operating systems. Then we broke down the core software layers from application to middleware to cloud. And we also learned about enabling technologies like OTA updates, AI ML, cybersecurity, and personalization. We discussed the software defined vehicle development lifecycle, including DevOps, model based design, and testing tools like Canoe, DSpace, and MATLAB. And we also discussed on real world case studies like Tesla, GM, Volkswagen, Carriad gave you context. And we wrapped up with a hands on mini project to bring it all together. Bottom line, software defined vehicles are not just the future, they are happening now, and you are ready to be part of it. Now, let's tackle a few frequently asked questions and important interview topics for software defined vehicle roles. Question number one: what tools should I learn first? Answer is start with the CAN tools like Vector Canoe, MATLAB Simulink, and basic AUTOSAR. Second question: do I need to know C or C++? Yes, C is a must for embedded roles. C++ or Python is a great for simulation and backend work. Third question: what is the difference between classic and adaptive AUTOSAR? Answer is classic is for real-time safety critical ECUs. Adaptive AUTOSAR is for high performance compute tasks like infotainment and ADAS. Fourth question: what are the top three interview questions? The top three interview questions are: explain the software defined vehicle architecture, what is OTA and how is it secured? Third question: how does SOME or IP middleware work in a zonal setup? Well, bonus point for you. No basic communication protocols like CAN, LIN, Ethernet, and how do you test them using tools like DSpace or ETAS? Well, finally, guys, here is your software defined vehicle learning roadmap and resources. Start with CAN communication basics using YouTube or free online tutorials. Move to MATLAB Simulink and do small modeling projects. Learn AUTOSAR, both classic and adaptive, through online courses. Practice tools like Vector Canoe, DSpace, and ETAS. For OTA and backend, explore Python, Linux, and cloud fundamentals like ASW. Well, some excellent platforms to explore are Udemy, Coursera for MBD, AUTOSAR, and embedded systems, Vector Academy for vector tools and Vector Canoe, GitHub. Look for some open source software defined vehicle or OTA projects or examples. Well, keep learning, keep building, and stay curious because the future of automotive is software first and it's waiting for you to drive it forward.